Problem 1.5. So it has two parts. Part A is where we need to verify that at high frequencies, the Wien's law is a good approximation to Planck's blackbody equation. So we have the Wien's law and we have Planck's blackbody equation. So before we prove anything, let's just write out what these are. Wien's law is connecting intensity to the frequency as well as the temperature, where A and B are empirical constants, and Planck's blackbody equation is a correction to Wien's law to accommodate the observations at lower frequencies. So that also connects the intensity with frequency and temperature. And Planck has showed that the constants A is equal to 2 pi h by c square. Sorry. Let me, 2 pi h by c square, and B is equal to h by k, where k is the Boltzmann constant. So now the question asks us to verify that at very high frequencies, the Wien's law is a good approximation to Planck's blackbody equation. So if we were to have very high frequencies in the Planck's blackbody equation, it would kind of reduce to Wien's law, right? So let's start with this equation. I equals a nu cubed by e to the b nu by t minus 1. So when the frequency is very high, this would imply that e to the power something that's very high is also going to be very high. So we can fairly assume that this very, very high value is going to be greater than, much, much greater than 1, right? So we can definitely approximate this to be just the exponential part, because this value here is much greater than 1. It doesn't matter whether we're subtracting a 1 from it or not. So we can assume that and approximate this whole term to just this term. Now let's put this in this equation. That will give us I equals a nu cubed divided by e to the b nu by t. And this is exactly the Wien's law. So we have proved that at very high frequencies, Planck's blackbody equation can be approximated to give us the Wien's law. Now let's work with problem 1.5b. Okay. In June 1900, Rayleigh applied the equipartition theorem of classical statistical mechanics to derive an equation for blackbody radiation that showed the radiation intensity to be proportional to nu squared times t. In 1905, Jeans pointed out an error in Rayleigh's derivation of the proportionality constant and corrected the Rayleigh formula to 2 pi nu square kt by c square. So this is the formula. Right now, we are asked to show that at very low frequencies, Planck's blackbody formula can be approximated by the Rayleigh-Jeans formula. So we know that the Planck's blackbody formula is given by I equals A nu cube divided by to the b nu by t minus 1. Yes, so this is the Planck's black body formula. And this formula is applicable whether we're dealing with high frequencies or low frequencies. And we have just showed in point in part A that at high frequencies, Wien's law is a good approximation. Now we have to show that on the other end, that is at low frequencies, Rayleigh-Jean's law is the Planck's black body formula can be approximated to the Rayleigh-Jean's law. That shouldn't be so hard. So at low frequencies, at very low frequencies, the term is also going to be very small. And when we have terms like this, where e to the power x is pretty small, we can actually use the Taylor expansion of e to the power x to simplify the problems at hand. So any exponential term, any e to the power x term can be written in Taylor expansion. So this term is exactly equal to 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus so on. This is an infinite sum, and any exponential term can be written in terms of Taylor expansion like this. So this is the Taylor expansion. Now we know very clearly that the frequency nu is very small, right? So in this case, if we were to expand this, let's first expand this into Taylor series. So that will be equal to b nu by t plus b nu by t whole square by 2 factorial plus so on, right? When nu is very small, nu square is going to be much smaller. Let's assume, let's look at a value of 0.1. 0.01 is a very small value, right? Now, what is 0.01 squared? It's 0.0001, which is much, much smaller than 0.01. We would even consider it negligible, depending on the units, of course. So when the frequency is small, is very small, the square of the frequency is going to be much, much smaller to a point that we can actually neglect the term. The frequency square is going to be a very small value that it's actually, when you multiply that with b by t, it's basically going to make the entire term's value much, much smaller. So we can approximate this term to be 0 and we can neglect it. And by a similar analogy, we can neglect all the higher order terms. So we can approximate this value to just be 1 plus b nu by t, because we're approximating all the higher terms, higher powers, to be equal to 0, right? So let's box this up. Now, okay, so now that we have established this, let's work with the Planck's blackbody equation. So I can write that as A mu q divided by the e to the power, the exponential term is approximated by this. We have just showed that. The 1 and the -1 cancel out. So we have the new, we get a new square by b. The t here is in the denominator of a denominator, so it goes to the numerator. So we end up with this particular term. Now we have a and b we don't have the Rayleigh-James equation in terms of A's and B's, right? So let's substitute for the values of the A and B, the constants. That would be 2 pi h of c squared times mu squared t divided by h over k, which I can write it as the h and h cancel out. So I can write it as 2 pi mu square t. The k is in the denominator of the denominator, so it goes to the numerator, c squared. Now I can just rearrange the kt terms there to write 2 pi mu square kt by c squared, which is nothing but the Rayleigh-James equation. So we have shown very clearly that at very, very small frequencies, the Planck's blackbody equation can be approximated to result in the Rayleigh-James equation.